All, this is Priyadharshini, working as an assistant professor in the Department of Artificial Intelligence and Data Science. Today I am going to discuss the topic on the mathematical analysis of recursive algorithms in the subject design and analysis of algorithms. Let's continue with the topic. So in this section, we'll see how to apply the general framework for analysis of algorithms to recursive algorithms. We'll start with an example often used to introduce the novices to the idea of a recursive algorithm. So let's start with the example. So recursive evaluation of n factorial. The example being, compute the factorial function f of n which is equal to n factorial for an arbitrary non-negative integer n. Since we all know n factorial is equal to 1 into n minus 1 factorial into n. That is n minus factorial into n for all n greater than or equal to 1. For example, if it is 5 factorial, we all know it is 5 into 4 factorial, that is 1 into 2 into 3 into 4 into 5. So in general we call for n factorial, it is n minus 1 factorial into n times. And also remember 0 factorial is equal to 1, which is by definition, and we can compute f of n is equal to f of n minus 1 into n with the following recursive algorithm. So let's see what the algorithm is. So algorithm's name is f of n to find the factorial function f of n recursively. The general description is to compute n factorial recursively, input being non-negative integer n, output the value of n factorial. So the pseudocode of this algorithm will be, if n is equal to 0, return 1, which is by definition, and f of n, to compute f of n, the factorial of an n number is f of n minus 1 into n. So here we will start with the general plan. So for simplicity, we will consider n itself as an indicator of this algorithm's input size rather than the number of bits in its binary expansion. And the basic operation of the algorithm is to multiplication, whose number of executions we denote m of n. Since the function f of n is computed according to the formula f of n is equal to f of n minus 1 into n factorial for all n greater than 0, the number of multiplication m of n needed to compute it must satisfy the equality m of n is equal to m of n minus 1 plus 1 for n greater than 0. Indeed, m of n minus 1 multiplications are spent to compute f of n minus 1, and one more multiplication is needed to multiply the result by n. The last equation defines the sequence m of n that we need to find. This equation defines m of n not explicitly, that is as a function of n, but implicitly as a function of its value at another point, namely n minus 1. Such equations are called recurrence relations, or for brevity, recurrences. Recurrence relations plays an important role only in analysis of algorithms, but also in some areas of applied mathematics. They are usually studied in detail in course on discrete mathematics or discrete structures. A very brief tutorial on them is provided. Our goal now is to solve the recurrence relation m of n is equal to m of n minus 1 plus 1, that is to find an explicit formula for m of n in terms of n only. Note, however, that there is not one infinitely many sequences that satisfy this recurrence. To determine a solution uniquely, we need an initial condition that tells us the value with which the sequence starts. We can obtain this value by inspection the condition that makes the algorithm stop its recursive call, that is, if n is equal to 0, return 1. This tells us two things. First, since the call stops when n is equal to 0, the smallest value of n for which this algorithm is executed, and hence m of n defined is 0. Second, by inspecting the pseudocode's exiting line, we can see that when n is equal to 0, the algorithm performs no multiplication. Therefore, the initial condition we are after is m of 0 is equal to 0, and the recurrence condition is m of n minus 1 is equal to m of n minus 1 plus 1. Before we embark on this discussion of how to solve this recurrence, let us pause to reiterate an important point. We are dealing here with two recursively defined functions. The first is the factorial function f of n itself. It is defined by the relation f of n is equal to f of n minus 1 into n for every n greater than 0, and f of 0 is equal to 1. The second is the number of multiplications m of n needed to compute f of n by the recursive algorithm, whose pseudocode was given at the beginning of this section. As we just showed, m of n is defined by the recurrences we need to solve. Though it is not difficult to guess the solution here when n is equal to 0 and increases by 1 on each step. It will be more useful to arrive it as a systematic approach fashion. From the several techniques available for solving recurrence evasion, we use what can be used the method of backward substitutions. The method's ideas immediately clear from the way it applies to solve a particular recurrences. After inspecting the three lines, we can formulate the general equation, that is m of n is equal to m of n minus I plus I. So this is how the algorithm is executed. So generally our experience with investigating the recursive algorithm for computing n factorial, we can now outline a general plan for investigating recursive algorithm. So the first plan would be decide on parameters indicating an input size, identify the algorithm's basic operation, check whether the number of times the basic operation is executed may vary on different inputs of the same size. If it can, the worst case, best case and best average case efficiency must be investigated separately. Set up a recurrence relation with the appropriate initial condition expressing the number of times the basic operation is executed. Solve the recurrence, or at least ascertain the order of growth of its solution by backward substitution or by another method. This is how a recurrence relation would be executed and its mathematical analysis would be